Hey everyone, welcome to another session of Ceerazzledazzle Physics. In this video, I'm going to be walking you through the entire magnetism topic. Let's get started. So, first of all, we have a bar magnet over here. A region around a bar magnet in which a magnetic material can experience a force is called a magnetic field. Over here, we can see that the field lines go out of the north, yes, out of the North Pole and into the south. And that's why I have the arrows over here. We know that there are three magnetic materials, iron, nickel and cobalt. And like poles will repel and opposite poles will attract. That means you put two north poles, they will repel, or two south poles, they will repel. If you put a north and south, they will obviously attract over here. Compasses and magnetic fields. If you were to be given a bar magnet, you can determine the direction of the magnetic field by simply taking a plotting compass, the ones with a needle inside which turn, and placing it at different points around the bar magnet. As you can see, when we place the compass at different points, the compass needle will follow the field lines. So as you can see over here, it follows this line over there, and this needle over here follows this line over here. So therefore you know that this one will be the south pole because the lines go in, and this side will be the north pole because the arrow is going away. So that's why they also call compasses south-seeking, because they're always pointing towards the south pole. Compasses and the Earth's magnetic field. If someone was to give you a navigational compass and you were to take it out, hopefully you recognize that it would always point to the North Pole. The reason why is because that we know that the magnetic field lines of the Earth will match up with the compass needle. So look, inside the Earth there is a bar magnet. You can visualize it as a bar magnet. And look, the field lines go out of the North Pole and therefore into the South. Yes. I know that's a bit confusing at the start because you're like, hang on a minute, isn't the North Pole at the top? Yes, the geographic North Pole is in fact the magnetic South, and the geographic South Pole is in fact the magnetic North. And we can verify this by using a navigational compass, because we know that when we take out a navigational compass, it will line up with the magnetic field, which is pointing upwards over here. Induced magnetism. So what happens when you are to bring an iron block next to a bar magnet? What will happen is the iron block will be attracted to the bar magnet. How does this happen? Well, first of all, it temporarily creates its own magnetic field within itself. So look over here, what happens is it makes the opposite pole. So if you have a south pole of a magnet facing it, it makes a north pole and the opposite end becomes south. And therefore it is attracted and therefore it moves across. This is only going to last for a temporary amount of time, and therefore this is not permanent. So therefore if you move the iron block away from it, eventually it will lose its magnetism. This whole process is called induced magnetism. Electromagnetism. So over here we have a circuit and we have a switch, and look, we have a wire going round, and look, it coils round over here. So the wire coils round, going up around the back, down around the front, coiling round over here. This is called a solenoid, a coiled wire. So we have a piece of iron next to it. Right now nothing's happening, the iron block is not attracted. But what happens when we press the switch? When we press the switch, hopefully we recognize that current will flow through the wire. Yes, current flows through the wire. Don't forget, the current will go out of the long positive terminal over here and all the way around over here. Now current passes through the wire. What will happen is a magnetic field will be induced within the solenoid. So look, we have a magnetic field induced within the solenoid. And obviously, if we have a magnetic field induced within the solenoid, it can now attract the iron block. So the piece of iron will move towards it over here. There we go. And obviously, this is a temporary magnetic field, because if I were to turn off the current, it will stop having a magnetic field. There are three ways to increase the strength of the magnetic field. Number one, by increasing the number of coils per unit length. So if I wrap them closer together. Number two, by increasing the current. And number three, by inserting an iron core through the coils, is the third way to increase the strength of the magnetic field. Electromagnets and the school bell. So this is a use of electromagnets. Over here we have a circuit, power supply over here. Then as you can see we have the solenoid over there. And this point is just like, let's say this is a metal arm, just a piece of metal, and there's a hinge point at the top. So there's a hinge point. The hinge point means that basically the metal arm can move, swing about that hinge point over here. So, and here's a gong and this at the bottom. What happens if we were to press the switch? Hopefully you recognize that when we press the switch, current will flow through the solenoid. Okay, current flows through the solenoid. We know that it's going to generate its own magnetic field, which is why it's in yellow. The magnetic field generated will therefore attract the iron bar. So it will then swing outwards and hit the gong, making the noise. Right, so as it hits the gong and it makes the noise, what will happen is the circuit will become broken. Okay, so if the circuit has become broken, what will happen is the magnetic field will therefore shut down, and therefore the metal arm will fall back into place once again, and then the whole process will start again. That's the reason why it gets hit repeatedly, again and again, due to electromagnets. The right-hand rule, so linking electricity and magnetism. So if you were to take your right hand, yes, your right hand, you were to hold it up, give yourself a thumbs up. So right now what's going to happen is your thumb is going to represent the direction of the current, and your fingers are going to represent the direction of the magnetic field. So the current goes up, the field is going this way. And obviously if I was to reverse the direction of the current, the field is going to swap direction. That's going to be important later on. Representing current into and out of the page. A circle and a dot simply means that the current is coming out of the board. Yes, the best way to visualize it is going to be, imagine if I was to throw a dart at you. First of all, if the dart is traveling towards you, you'd see a dot. That means that it's coming towards you. If the dart was moving away from you, you'd see the fins which are crossed. Hence why we're going to use a symbol of circle and a cross to mean into the board or moving away from you. So circle and dot means out, and then circle and cross means into the board. So if you were asked the following, so if somebody was to draw the current going into the page, so circle and cross, which way is the magnetic field? Well, take your thumb, point it into the page right now, or into the screen, and therefore you can see it's going to go clockwise in that direction. And if you were to have the current pointing towards you out of the screen or out of the page, first of all, take your thumb, point it towards you, and we can see the current is going to go anti-clockwise over here. So this is how we can determine the direction of the field based upon the current. Force on a conducting wire within a magnetic field. So over here we're going to have a circuit. Yes, so look, we've got a cell over there, switch, and a wire. Yes, connected all the way around over here. We're going to then place that within a horseshoe magnet. Basically, it's a north and south pole normal bar magnet, we're just bent into a horseshoe shape. First of all, recognize that the magnetic field lines are going to go out of the north into the south. Yes, so the magnetic field lines are going to go from the north pole to the south pole. If you were to then press the switch, what will happen is current will flow through the wire. When current flows through the wire, we know that every single wire which has current flowing through it will generate its own magnetic field. So the magnetic field is therefore induced around the wire. So now there's going to be a magnetic field from the permanent magnet, from the horseshoe magnet, and there's going to be a magnetic field from the wire. Both of them will interact, and therefore the wire will experience a force. So both of them will interact and the wire will experience a force. We can use Fleming's left-hand rule to determine the direction in which that wire will move, which we'll do in a moment. Fleming's left-hand rule. Fleming's left-hand rule can be used to determine the direction of the force on that conducting wire. So first of all, take out your left hand now. So best way to do it is going to be FBI. F stands for direction of the force. B stands for direction of the magnetic field. Over there, I'll put down magnetic flux density, but still the direction of the field, and I is going to be the current. Notice they're all 90 degrees towards each other. You must have the wire perpendicular to the field, and therefore you will get a force. So in this diagram over here, you can clearly see that the field is going across, yes, and therefore we know the current's going into the page. Make sure you can see that, it's going into the page, therefore the force is down. And then at the bottom, I've got 1, 2, 3, 4 more examples in which I've drawn the sideways on view. So obviously over here we can see the current's going in, so look, verify it, we can see the force is down. Pause the video and make sure you can try these examples yourself. More practice on Fleming's left-hand rule. So over here I've got 1, 2, 3, 4 diagrams, and they're slightly different. Look carefully, they're slightly different. What you're going to do is you should be able to take out your left hand and verify the direction of the force. Don't forget, when you're using Fleming's left-hand rule, you should do the field direction first, then rotate your hand for the current. So do the field first, rotate your hand for the current, and then you can determine the direction of the force by which way your thumb is pointing. Force on a conducting wire within a magnetic field, and F is equal to B. Right, if you actually want to calculate the value of the force, first of all we can use the following formula. F is equal to BIL, where F is the force, B is the magnetic flux density, I is the current, and L is the length of the wire within the field. The force is measured in newtons, magnetic flux density is measured in Tesla, the current is in amps, the length of the wire is going to be in meters. It's only going to be this length within the field over here. The DC motor, right, so this is going to be the physics behind how we have a motor spinning. So there is a coil of wire over here, and it's the square coil right now. It's a square coil of wire. We're going to place it in between a north and south pole. Right, so that's my wire, A, B, C, and D. And we're going to pass current through the wire over here, through A. We can see it's going to go to the left, up, then from B to C, down, and then back again over here. So now there's a current flowing through the wire. Right, we know there's current flowing through a wire, and parts of the wire which are perpendicular to the field will experience a force. So I've drawn this a bird's eye view of this over here. Look, so this is a north, and that's that wire, just a bird's eye view. We can hopefully see that A to B, the current is perpendicular to the field, and C to D, the current is also perpendicular to the field, but they are both in opposite directions. So A to B, there will be a force downwards, verify it using Fleming's left-hand rule. C to D, there's a force pushing it upwards. And therefore, if AB is moving down and CD is moving up, the whole thing will rotate. So the whole thing will rotate here, and that's going to be the origin of the physics behind a DC motor. Right, so the DC motor, this is the full diagram right now. So first of all, there is a split ring commutator over here. So imagine a ring which has now been split. That's going to be the split ring commutator. And then there's a carbon brush over here. So current's going to pass in from this side and look, going to enter via the carbon brush. The reason why we put a carbon brush is therefore that there's going to be a connection, but it can rotate freely. So as this rotates round, there will always be a connection because the brush can just swap round to the next terminal. As the coil rotates, we notice that the split ring commutator on the right is going to obviously get to the position on the left-hand side over here and will rotate round. This ensures that the current always enters from the same side and therefore ensures a full complete rotation. The generator effect is the process of generating voltage from the movement of magnets into coils. Yes, you either move the magnet into a coil or the coil into a magnet, and this is known as the generator effect. When a wire or coil experiences a changing magnetic field, a voltage is induced. So when a wire or a coil experiences a changing magnetic field, a voltage is induced. And I've got two diagrams right now. So the first diagram, we've got a voltmeter and we've got a solenoid over here, just a coil of wire. We notice that when we push a bar magnet into it, we'll get a voltage one way. Yes, so a voltage is induced. The reason why is because the coil is experiencing a changing magnetic field. Because initially there wasn't a magnetic field going through it. Then as you put the bar magnet in it, we notice that the coil experiences a changing magnetic field. As you move the bar magnet out, notice that the voltage will actually swap direction. So if you move the bar magnet in, the voltage goes one way. If you move the bar magnet out, the voltage goes the opposite way over here. So the voltage can be induced by moving the bar magnet into the coil. In order to get a greater magnitude of the voltage, to get a greater value of the voltage, you can simply move the magnet faster, or you can use stronger magnets, or by increasing the number of coils per unit meter. So by increasing the number of coils, you would therefore generate more of a voltage if you move that bar magnet in. Second method to generate voltage is the following. So over here, rather than moving the bar magnet into the coil, we're going to move a wire within a magnetic field. So look, we've got our horseshoe magnet over here, and look, we've got a voltmeter and a wire in this diagram. There is no power supply. You're going to take the wire and you're going to move it up and down within the magnetic field. When the wire moves within the magnetic field, we notice that it will cut the magnetic field lines, and therefore it will generate a voltage. So moving the wire upwards, we'll get a voltage one direction. Moving the wire downwards, we'll generate a voltage in the opposite direction over here. There are three ways to increase the size of the voltage induced. Number one, it's going to be by moving the wire faster. Number two is by using stronger magnets. And number three, by putting more wires within the field. So if you put more wires within the field and you move them all, you will generate a greater amount of voltage at the end. So don't forget, you need to be experiencing a changing magnetic field to induce a voltage. Generators. So over here we have a DC generator, also called a dynamo. So a DC generator, the DC stands for direct current. Look at this diagram, it looks almost similar to the DC motor, but instead of a power supply, there is a voltmeter. We still have the split ring commutators and we still have the carbon brushes. So the difference between this one and the DC motor is that in a DC motor, you're passing current through and it's getting forces and they're turning. Now, in this diagram, you are going to turn it. You are going to turn that square coil within the field. So you must turn the coil within the field and a voltage will be induced. And don't forget, because we've got the split ring commutators, it only produces DC voltage. So therefore, every half turn, so when this rotates halfway, we get to this point. Rotating it one full rotation, we do it and we get to this point over here. AC generators. AC generators are not the same as the dynamos. The reason why is because they do not have the split ring commutator. They have a slip ring over here. So look, we've got two rings over there, complete rings this time. One part of the wire is connected to this ring. The other part of the wire is connected to this ring over here. They never swap over. They never swap over. So what happens is now when the coil rotates, is simply, rather than getting a DC voltage out, we then get an AC voltage being produced. We get an AC voltage because there is no longer the swapping of terminals with the carbon brushes, which we had previously with the DC generator. So this one, the split ring, the generator, which is AC, will only have a slip ring over here. Loudspeakers. How do loudspeakers work? Right, so this is quite tricky the first time you look at it. So first of all, there is a bar magnet over here, and north and south over here going around, and we have a speaker cone in between. There are coils wrapped around the speaker cone. So what we're going to do is this. You're going to pass current through the coil. Right, so when you pass current through the coil, what will happen is it will generate its own magnetic field. But there is already a magnetic field from the permanent magnet. The magnetic field around the coil over here will interact with the magnetic field from the permanent magnet. The two fields interact, therefore it causes a force to be experienced by the cone, and the cone will move outwards. Okay, then how would the cone move inwards? Don't forget, it's a loudspeaker, it should pulse. So in order to move the cone back inwards, all you've got to do is simply reverse the direction of the current, and therefore it will experience a force in the opposite direction, and therefore it moves back in. That's the reason why you have the AC supply for a loudspeaker. Microphones. Microphones are a bit different. So microphones, you're going to speak into the microphone and it's going to generate a voltage. So look over here, we've got a microphone receiver and we've got it within a magnetic field once again. So when the sound waves come in, it pushes the microphone receiver into the magnetic field. So it pushes all these coils into that magnetic field. These coils therefore experience a change in magnetic field, and therefore a voltage is induced. So the coils of wire enter the magnetic field, and therefore because they are experiencing a changing magnetic field, a voltage is induced. So this one is the generator effect over here, because you're going to be generating voltage. So obviously as the sound wave goes in, it generates a voltage, and as you move the coil out again slightly, it generates a voltage in the opposite way. So as a sound wave comes in, the movement of the coil is going to obviously match the frequency of that sound wave. Therefore, it converts the sound waves into an electrical signal. Make sure you understand the difference between the loudspeaker, which is basically the motor effect, because you need it to make motion, and the generator effect is going to be in the microphone because you're going to be generating the voltage, because that wire is experiencing a changing magnetic field. Transformers. So, basics of transformers. First of all, if you want to transmit electricity from a power station to your home, surely you need a very large cable, yes? But if you were to use a high current to do this, what happens is when high current passes through a wire, it heats up, and when the wire heats up, energy is wasted. This is very inefficient. Therefore, we use transformers. Transformers, there are two types. Number one, there's a step-up transformer and there's a step-down transformer. Don't forget, we're going to go from the power station to your home. So first of all, high current comes out of the power station at a low voltage. The step-up transformer is going to step up the voltage to reduce the current. So it steps up the voltage to reduce the current. And therefore, the electricity is transmitted at low current but high voltage. Then when it gets to the step-down transformer, what's going to happen is it's going to step down the voltage to increase the current. So it steps down the voltage to increase the current. How does this work? Well, you can use the power equation to visualize it, because as you increase the voltage for the step-up transformer, the current decreases for the power to remain constant. And for the step-down transformer, as you are decreasing the voltage, yes, therefore the current is increased again to keep the power constant. Transformers and how they work using magnetism. So this is going to be the structure of a transformer. It is a giant iron block over here, and it's got coils of wire around the first terminal over here, and it's got coils of wire wrapped around the second terminal over here. It's made out of iron, everyone. This one is called the primary coil, this is called the secondary coil. The wires themselves are insulated. The wires are insulated, and there's a alternating voltage which is going into the primary coil and a voltmeter at the end on the secondary coil over here. Step-up transformer. To identify a step-up transformer, we know that there are going to be more coils on the secondary coil than the primary. For a step-down transformer, we know that's going to be more coils on the primary than the secondary. So look, we're going to have NP represents the number of turns on the primary coil, NS represents the number of turns on the secondary coil. How do transformers work? So first of all, you pass current through the primary coil. Hopefully you recognize that when current passes through the primary coil, a magnetic field is induced. Now the magnetic field is induced, don't forget this is made out of iron. Therefore the magnetic field can flow through the iron core right now. Excellent stuff. As the secondary coil is now experiencing a changing magnetic field, a voltage will be induced. So look over here, we can see that as the secondary coil experiences a changing magnetic field, a voltage will be induced due to the generator effect. And that's why we have the voltmeter at the end over here. In order to ensure that the magnetic field is constantly changing, I simply have to reverse the current in the primary coil. Because when I reverse the current in the primary coil, it swaps the direction of the magnetic field. You need to have a changing magnetic field in order to have a voltage being induced constantly. Transformer equations. There is an equation to link the number of turns in the primary and number of turns in secondary, and the voltage in the primary and the voltage in the secondary. It will be the following. NP over NS is equal to VP over VS, where VP is the voltage in the primary coil, VS is the voltage in the secondary coil, NP is the number of turns in the primary coil, and NS is the number of turns on the secondary coil. There is another formula relating the current and voltage in both the primary and secondary coils. First of all, the power entering it must be the same as the power out. We also know that power is equal to current times by voltage. Therefore, the current in the primary times by the voltage in the primary will be equal to the current in the secondary times by the voltage in the secondary. That's it for another session of Ceerazzledazzle Physics. If you want me to go through different parts of this video at a slower rate in more detail, then click on the playlist in my description and you should be able to solve all your problems. Don't forget to like and subscribe and comment below if you get stuck. I'll do my best to answer all queries. Ciao, ciao and goodbye.